All right, here we are for Math Tidbits number 4. This is going to deal with the scalar product in component notation. I thought about doing vector and scalar products together, but simpler to split them. So, and actually, you'll be using scalar products long before you're dealing with cross products. So, to keep the two separate is probably a good thing. All right, so you'll recall that if I have vector A and vector B, with theta being the angle between them, that the scalar product A dot B is given as the product of the magnitudes A and B times the cosine of theta, where theta is the smaller of the angles between the two. You could measure the angle between A and B here, or all the way around here, and the smaller one is the one that we need to deal with here. So that's one expression of the scalar product. Now, however, now that we have a means of writing down in component notation these two, A and B, as ax I hat plus ay j hat and bx I hat plus by j hat. We have another way of expressing the scalar product between these two vectors. That is, if I want to take A dot B, I will write it as A sub x I hat plus A sub y j hat dot B sub x I hat plus B sub y j hat. And now let's work out all of the four products here. I have A sub x B sub x I hat dot I hat plus A sub x I hat dot B sub y j hat plus A sub y j hat dot B sub x I hat plus A sub y j hat dot B sub y j hat. Now, of course, I defaulted to writing things a little more simply. Let's take all of the scalar stuff out front. So I'm just going to do with all the other three terms what I did with this one. So I've got ax bx I hat dot I hat plus ax by I hat dot j hat plus A sub y B sub x j hat dot I hat plus A sub y B sub y j hat dot j hat. Now, in order to resolve this, I need to know what are all of these unit vector dot products. Well, those are very simple because we have some easy rules of thumb. Perpendicular vectors have 0 scalar product, and parallel vectors have scalar product equal to the magnitude of one times the magnitude of the other. So that makes things like I hat dot I hat easy, and I hat dot j hat similarly. Namely, they are 1 and 0. And remembering that the order of these vectors in the scalar product doesn't matter. J hat dot I hat is 0. J hat dot J hat is equal to 1. And same thing would be true for K hat dot K hat. And same thing here would be true for I hat dot K hat, or J hat dot K hat, or any of the other ways of writing that product of those disparate vectors. So because of this, then, A dot B is written as AX BX plus AY BY. These other products with the I hat dot J hat or J hat dot I hat, which is 0, those drop. So now I have a new expression. There's expression 1, and there's expression 2. What this means is you have a very easy way, if you know the vectors by component, you've got an easy way to get the angle between the two vectors. And now, what I would like to talk about is what happens in 3 dimensions. 3-dimensional angles between two vectors are hard to even visualize, let alone calculate, except that our technique now is going to involve the scalar product. So if I want to know the cosine of the angle between A and B, so if I've got A and B in space in 3 dimensions, then the cosine of the angle between the two vectors will be equal to A sub x b sub x plus A sub y b sub y plus A sub z b sub z divided by the product of the magnitudes AB. Just taking these two equations, generalizing to 3 dimensions, and then solving for the cosine of the angle. This is incredibly useful. If I've got vectors that I've given you, and we'll do an example here. If I've got vectors that I've given you that are 3-dimensional vectors, then you can get the angle between the two vectors in this manner. Okay? So let us suppose, and I think we can do this on this one sheet. Let us suppose that A is equal to 5 meters I hat minus 2 meters J hat plus 4 meters K hat. And vector B is equal to 3 meters I hat plus 1 meter J hat plus 7 meters K hat. And I want to know the angle between these two vectors in 3 dimensions. Again, trying to visualize this in 3 dimensions is kind of tricky. Trying to figure out what the angle would be is really tricky. However, doing our work with this equation that we've derived from the 2 different expressions of the scalar product makes this really, really, really easy. So the angle theta between the two is going to be the inverse cosine, or arc cosine, if you will, of, and now it's just a matter of the appropriate components. So we got 5 meters times 3 meters, that's AX times BX, right? So that'll be 15 meters squared. Don't worry about the fact that it's meters squared. There will be meters squared in the denominator also, so that there's no units of the argument of the arc cosine. Minus 2 meters squared plus 28 meters squared, right? And now I need to divide this by the magnitudes of A and B. So I have to do a little calculation, the magnitudes of A and B. So the magnitude of A is going to equal the square root of 25 meters squared plus 4 meters squared plus 16 meters squared, right? Okay, and that should equal 25, and 20 is 45, the square root of 45 meters. Okay, or the square root of 45 meters if you want. And B likewise will be the square root of 9 meters squared plus 1 meter squared plus 49 meters squared, or the square root of 59 meters. So I just need to write this down, multiply this here. Square root of 45 times the square root of 59, and then I'll have a meter contribution from each. Okay? I'm more or less done now, because now I just got to plug in those numbers, and what I'm going to get here looks to me like about 37.3 degrees. All right, never would have guessed that angle, right? We're close to it. I might have looked at this and said, yeah, it's going to be reasonably small, but this is a really, really nice tool for you to get the angle between vectors. Okay, and it just comes out of our basic definition of the scalar product, our basic understanding of perpendicular, mutually orthogonal or mutually perpendicular unit vectors. We use that to derive a very nice result for the scalar product in terms of the components of the two vectors we're multiplying, and then it's a piece of cake after that to get the angle. All right, next video will be the vector product in component notation, and look forward to doing that for you.